Hello and welcome to today's quantum mechanics tutorial. I want this to be a little bit unstructured. We're not actually, in this particular tutorial, we're not going to be going through particular questions in the notes, but rather I want to discuss two very deep things. The first is about the marriage of relativity, the theory of special relativity, as in Einstein's relativity, with quantum mechanics. And the second is about this controversial quote, or more precisely a misquote, from Stephen Hawking for discussion. And I'd like strong views on both sides, both for and against this question. But let's begin with the first thing about the question of marrying relativity with quantum mechanics. Relativity as in the special theory of relativity. And the amount of relativity that we need to begin to answer this question is what you learned in first year, which I'll revise briefly. But let me begin with the question. If you pick a random person off the street and they don't know any mathematical physics, and if you were to ask that person on the street to summarise the essence of the theory of relativity in one sentence, what might they say? Summarise relativity in one sentence. Random person on the street.
Weird stuff happens when you tend towards the speed of light.
So weird stuff happens when you tend towards the speed of light. Beautiful. Other answers you might get if you asked a random person off the street what relativity means. And you'll see, by the way, why I'm talking about relativity in the quantum class soon. Trust me, it's relevant. Any two or three word answers come to mind? I don't know. Beautiful. Actually, that's probably the best one. The average person won't know the essence of relativity. But if they were to say everything's relative, some, maybe a small fraction, would say everything's relative. And from one perspective, that might seem quite superficial. So granted that the most likely honest answer would be I don't know. They might also say E equals mc squared. A more profound, or a person with deeper knowledge might say that bizarre things happen when you approach the speed of light. But one common answer would be that everything is relative. Now, in my opinion, this is the most profound answer, whether you're a person on the street or someone who is deeply imbued in the theory of special relativity. This actually contains the essence of it. Relative in what sense? Question, you do physics according to your way of describing the world. How do we describe the world? How do we describe the stage on which physics is done? Well, you give me a position and you give me a time. You give me a coordinate system, an XYZ coordinate system, and you give me a clock, and I'll be able to do physics. And you can describe the physical world, wave functions filling this room, light filling this room, according to your coordinate system, your XYZ t. But if I'm moving relative to you at constant speed, let's say, I have an XYZ, that's it there, and I have a t, which is my watch, and I can describe physics from my perspective. And the question is, should the laws of physics be the same for you as they are for me? Each of us have a different perspective. I'll do my physics relative to my frame of reference, my XYZ t. You'll do your physics relative to your frame of reference, your XYZ t. And the statement everything is relative just says that the laws of physics should be the same for you and for me. Yeah, the laws of physics should be the same in either of these frames of reference, either of these XYZ t's. Now, special relativity says that the laws of physics are the same in all inertial frames. These are non-accelerated frames. Ignoring the fact that the Earth is going around the Sun, you're approximately in a non-accelerated frame. I'm approximately in a non-accelerated frame. The laws of physics should be the same for both of us. That's the essence of special relativity. General relativity takes this a step further and says, bugger non-accelerated frames, no frame of reference is privileged. If I want to jump up and down and move from left to right, and I want to do my physics from the perspective of this crazy frame of reference, then the laws of physics for me should be the same as the laws of physics for you. General relativity says the laws of physics should be the same in any frame of reference. Crazy though those references frames might be. And that's a very, very profound thing. There is no privileged frame of reference. Now, restricting ourselves to special relativity, that statement that the laws of physics should be the same in every non-accelerated frame of reference makes it clear that in some sense special relativity is special. I mean, in what sense is that statement, the laws of physics must be the same in all frame of reference? I'm actually having trouble asking the question. So suppose I study, I don't know, pick a subject in physics. I'm lost for words. Optics, beautiful. So suppose I want to study optics, and I say optics is, I'm an optical physicist, optics is the best subject, everyone should study optics. And you might say, well, I actually don't care about optics and I don't want to learn it, and that's fine. But then I say, okay, I'm a relativity person, and relativity is special. There's something special about relativity. Relativity is somehow more special than optics. In what way is relativity as captured by this principle more special than optics? The clue is that sentence. All the laws of physics are the same in every non-accelerated frame of reference.
It underpins it.
It underpins, absolutely. And that's the key thing. When I say, or when Einstein says, the laws of physics are the same in all frames of reference, that's unlike optics. Optics is one area of physics, sure, a broad and interesting area with many connections. But when you say all of the laws of physics are the same in every frame of reference, that's an underpinning statement. It underpins all physical theory. And that's why I'm talking about relativity in a quantum class. If all the laws of physics must be the same in all non-accelerated frames of reference, then relativity must impact upon every law of physics, including quantum physics. And so this begs the natural question of how to marry relativity with quantum. Now, when we obtained the Schrödinger equation, we did so by writing down a law of Newtonian mechanics, applying the Schrödinger correspondence rules, and hence obtaining the Schrödinger equation. Let me briefly revise that now. So we wrote down the law for the energy of a particle. It's kinetic energy, which is p squared on 2m. And p squared is the magnitude of the momentum vector p squared, or p dotted with itself, plus potential. We then applied the Schrödinger correspondence rules. We replaced energy with an operator, which was IH cross d by dt. And then we replaced momentum with an operator. We threw that into our relationship here, energy equals p squared, which is p dot p, which is minus h bar squared, grad squared. We had a potential. We got our 2m. So we applied our Schrödinger correspondence rules to this expression. We post-multiplied by a wave function. And we got the Schrödinger equation, the time-dependent Schrödinger equation. Now, I want to consider a simpler world which has no background potential. So this is just vacuum, just as a special case. This is the Schrödinger equation in the absence of any external forces. The key point here is that this is an equation of Newtonian mechanics. This equation is not consistent with relativity. What's the simplest argument you can give, the most direct argument you can give for why Newtonian mechanics is inconsistent with special relativity? And the clue is the earlier comment. The clue is an earlier comment made by one of you.
You can't accelerate things infinitely to an infinite speed.
Beautiful. You can't accelerate things to an infinite speed. When you write F equals ma, if the force is uniform, and the mass, of course, in inverted commas, is uniform, uniform force means uniform acceleration, which means if you push for an arbitrarily long time, let it start from rest in 1d, the velocity will be the force, the acceleration times the time, which will be ft on m, and this will become infinite if you push for an infinite time. So F equals ma implies uniform force, uniform acceleration. For an arbitrarily long time, you can go arbitrarily fast, but things get funny when you approach the speed of light. This idea that speeds can become infinite if you push for long enough is inconsistent with c as a speed limit. So this object here is not consistent with relativity because this is a cornerstone of classical mechanics. And classical Newtonian mechanics is not consistent with relativity. Hence, any equation derived from it will not be consistent with relativity. Again, theories have domains of validity. If you have a relativistic electron, an electron moving near the speed of light, this equation, or with a speed which is a non-negligible fraction of the speed of light, this equation won't cut it. So if, for example, or if, as another example, if you have some particle in the Large Hadron Collider, which is created with a speed that's 99.999999% of the speed of light, this equation is not going to work. So the question is, how do we come up with a relativistic form of quantum mechanics? Now imagine it's about 1925, you're Einstein or Fock or Schrödinger or Dirac, and you're asking these questions. How do you come up with a form of relativity, a form of quantum mechanics, that's consistent with relativity? How would you do so? And I'm not trying to test your ability to remember stuff from first year. The answer's somewhere here. It's just a plain English answer, not memorising any fancy equations. How would you construct or begin to construct a version of quantum mechanics that is consistent with relativity?
Start with relativistic energy and then do what you did before, changing to operators.
Beautiful. Start with a relativistic version of this expression and then do what you did before regarding the use of the Schrödinger correspondence rules. Now, the equation which corresponds to this in relativity is the following. And I'm just using p squared as a shorthand for p dot p. So p squared is a shorthand for p dot p. So this is the relativistic version of this Newtonian expression. And then, as you say, we apply the same rules as before. So let's do that. Let's take this expression which relates so you have a particle moving in free space. That particle has a mass m. P is the magnitude of its momentum and c is the speed of light. Now we need to be a bit careful about what we mean by mass, because here's the most famous equation in all physics. E equals mc squared. Fair enough. What this says to me might seem a bit peculiar. It's sometimes said that this speaks of the conversion of mass into energy. That's wrong, right? Let me give you an example. So let me say something and then I want you to pick it apart. Here's a nuclear bomb. It has a mass of m. The nuclear bomb blows up. So here's a uranium atom inside a nuclear bomb. After the bomb blows up, it decays into a barium nucleus and a krypton nucleus. And both of those things are moving with equal and opposite momenta. If I take a uranium nucleus and weigh it, it'll have a certain mass, a stationary uranium nucleus. If I take the stationary barium nucleus and weigh it, it'll have a certain mass. Ditto for the krypton. And if I take these stationary nuclei and add their masses, I'll get a so-called mass defect, that this mass is bigger than this one. Hence, mass has been converted into energy. That energy is the kinetic energy of the nuclei together with any photons that are being created. That statement, even if you've been told it in high school, is wrong. What don't I like about that statement? That mass has been converted into energy. So let's have a roundabout way of answering this. Suppose I was to say that we're very arrogant. We measure our length in metres, which is, give or take, 1 is roughly equal to 2 in the back of the envelope calculation, and don't quote me on that. 1 metre is roughly the height of a person. It's certainly a distance that we can directly apprehend. A second is roughly the period of a heartbeat. So a metre per second, for example, is a foot per heartbeat. Sorry, a footstep per heartbeat. The key point is, and kilograms can also be directly apprehended by us as humans. The point is, we've chosen units of mass and time and length, which are easy for us to apprehend. Suppose I was to say, instead of measuring all speeds in terms of footsteps per heartbeat, which is a pointlessly human-centred unit system, let's instead say, well, c is a special speed. Let's work in a different system of units, which you might call natural units. In which all speeds are a fraction of the speed of light. So when I say the speed is 0.1, I mean 10% of the speed of light. Instead of measuring all speeds relative to 1 footstep per heartbeat, let's instead measure all speeds relative to the speed of light. And so again, any speed is going to be relative to the speed of light. A speed of 1 will now mean that c equals 1. Sorry, a speed of 1 will mean that you're travelling at the speed of light. So E equals mc squared becomes E equals m in this better system of units. What does that equation mean to you? It's the simplest equation you'll see in this course. E equals m. If two quantities are equal, then they're the same thing. So energy and mass are the same thing. Conservation of energy is the same thing as conservation of mass. To convert energy into a mass, or mass into energy, is to ignore the point, which is that energy and mass are the same thing. But the mass of this is not equal to the mass of this plus the mass of this. What's going on?
One is at rest.
One is at rest, absolutely. Energy is mass, right? I have a mass of m. If I'm moving relative to you, I have more energy, and if energy is mass and my energy is increased, then my mass is increased. The moving chalk has more mass than the stationary chalk. The moving nuclei are heavier than the stationary nuclei. This is why we often speak of rest mass in relativity. What's its mass when it's stationary? Because to speak of mass is ambiguous. You say this chalk is heavier than I say it is, because it's moving relative to you, has more energy, hence has more mass. It's stationary relative to me. So mass is conserved. The mass of the stationary uranium nucleus is equal to the mass of the moving barium nucleus, the moving krypton nucleus, plus the mass of any light that's radiated. Sure, if you bring these to rest, you'll reduce their energy, hence you'll reduce their mass, and you get this so-called mass defect. But energy is conserved, mass is conserved, they're the same thing. I'm just asking myself the question why I've said this. Why I've said this is because this mass is ambiguous. I'll put a subscript 0 on it. This means the mass of an object, let's say an electron, when it's at rest. Excellent. Now let's take your prescription. We're going to take the relativistic formula, which relates energy, momentum and mass, and apply the Schrödinger correspondence rules to it. So let's do it. So I'm just going to write the equation out again. By the way, this was covered very briefly in first year. But for now, we can just take this on faith, or better still, learn how to drive it yourselves. That's beyond the scope of the course. We want to apply the Schrödinger correspondence rules to this. What do I do?
Same way we did last time.
Yeah.
Using I h bar dt.
Yep, fantastic. Same as I did last time. E is I h bar d by dt. So E squared will be, beautiful, minus h bar squared d squared by dt squared. By the way, we've got a second order equation in time, something that I want to touch on soon. P squared will become close. So this is P squared will become, it's close. P squared will become negative h bar squared grad squared. And we have our c squared coming along for the ride. We've got this.
Why would it be positive? The p squared, c squared.
So the question is, won't the p squared, c squared be positive?
Oh,
Yeah, so why is it negative? Because the first time I did this and the second time I made it positive, it is true, it is negative. Why is p squared, c squared have a negative out the front?
The negatives cancel and you get I squared.
Yeah, beautiful. The negatives cancel and you have an I squared. So let's do this explicitly. So this is p squared. And p, because you square a number and you get a positive, right? That's so deeply ingrained in your head. P dot p is a dot product of the vector with itself. It's never going to be negative. That's not true in this case, because for exactly the reason described, p is minus IH cross grad, dotted with minus IH cross grad. The negative and the negative absolutely cancel. The I and the I get together to give a negative sign. The H bar and the H bar squared, and grad squared. So even though your instincts tell you that p dot p is never negative, if p are vectors, when they're complex operators, you can pick up this negative sign. So back to this, we have this operator equation. What do I do next? Beautiful. I need to put a wave function in there. So congratulations, you've just won 2/3 of a Nobel Prize. Good stuff. This equation, by the way, was first written down by Einstein, who threw it in the rubbish bin. It was written down by Schrödinger before he wrote down the Schrödinger equation. He too threw it in the rubbish bin. Fock wrote it down. He threw it in the rubbish bin. Klein and Gordon wrote it down. They were a bit worried about it, but they published it. So it's called the Klein-Gordon equation. And so this is an equation of relativistic quantum mechanics, and it's used every microsecond on the Large Hadron Collider to describe particular classes of particles, so-called spinless particles. Now we'll talk about spin at the end of this course. The point is that this is a relativistic form of the Schrödinger equation, and it's used, as I said, every microsecond. I wasn't being flippant that all the data on the Large Hadron Collider is taken with high-speed electronics. That those high-speed electronics make billions of measurements per second. In fact, billions of measurements per thousandth of a second. And when they have spinless particles, or particles for which the spin can be ignored. And we'll talk about spin in due course, but the point is it's an attribute of fundamental particles, and certain particles have zero spin, such as neutral pions, certain mesons, and so on. So there are plenty of exotic particles that obey this thing, Klein-Gordon equation. Before I go on, are there any questions about anything that we've developed so far regarding relativity and quantum mixed together? Cool. You might be asking yourself, why did Einstein throw this in the bin? Why did Schrödinger throw this equation in the bin? Why did Fock throw this in the bin? By the way, if you haven't met the name Fock before, a famous Russian mathematical physicist. The reason they threw this in the bin was because they didn't like this. They didn't like the d squared by dt squared. And let me tell you why they didn't like it. In fact, you're going to tell me why you don't like it, and I'm going to give you some clues. My first clue is that we argued earlier. So I'm going to give you two clues, then I'm going to ask you to read Einstein's mind and answer the question, why did he throw it in the bin? Yep.
Wave function equals 0.
Because the wave function equals 0. Can you elaborate on that?
When you derive it twice,
Yeah.
the coefficient term will be 0.
Yeah.
So then the whole equation will be 0.
So when you differentiate it twice, why would this vanish when you differentiate twice?
Because the wave function will equal 0.
Actually, that statement's incorrect. But how do you come at that statement though? So why would the second derivative be naught? Yes. So in general, the second derivative won't necessarily vanish. There'll be certain circumstances in which it does, but in general, it won't. So if I have some wave function which is varying with time, and let's choose a particular point in space. So let's fix r to be equal to r naught, and let's consider, for example, the real part of the wave function. So you're at this particular point r naught in space. The real part of the wave function, I just write the real part because I can draw it on a graph. I could do the same thing for the imaginary part. And at that given instant of time, the real part of the wave function might have some value. If you wait some infinitesimal time later, the wave function's real part will in general evolve a little bit. And so to an excellent approximation, you have a straight line. And so in that sense, you might expect that if you were to differentiate it again, because this is a second derivative with respect to time, if you were to differentiate this once, you get the slope, and twice you get 0. So I can see now why it's natural to consider the wave function's second derivative to be naught. But if we evolve for longer times, then if we consider longer times still, then in general this won't necessarily be a straight line. It will be a straight line, absolutely, for very, very small time intervals, but for longer time intervals, it can be better approximated by a parabola, the next order in the Taylor series. And so it's actually the coefficient of the t squared term that would pre-multiply this psi. So let's go back to the question of why we don't like this equation, or why Einstein didn't like it. Wave function gives total knowledge of the system. And there's always nothing wrong with being wrong. So does anyone want to have a crack again at reading Einstein's mind? In fact, reading a mistake in Einstein's mind. No problem. Here's a piece of string. So here's another clue. Here's a piece of string. And I tell you that at a given time, that's what the string looks like. So it's a string connected between 2 points on a wall. That string is going to be described by some height, h, and that height will be a function of position x. There's an x-coordinate system here, and that height will also be a function of time. And I tell you that this is what the string looks like at time t equals naught. And I then ask you, what does the string look like in 1 second? What's the answer to the question? I've told you the shape of the string. I've told you the height as a function of position at some particular time, let's say t equals naught. I've told you that. There you go, there's an initial condition. Tell me what the string looks like in 1 second. What would you tell me?
You need the initial velocity as well.
Beautiful, you need the initial velocity as well. There's not enough information here. The answer to the question, tell me what the string looks like in 1 second. Given this single initial condition, the answer is I don't know. I haven't been given enough information. You also need to tell me the velocity, h dot, which is dh dt. So you need to tell me 2 initial conditions. The differential equation obeyed by waves on a string for small h is the following. It's the wave equation. The fact that you need 2 initial conditions is directly related to the fact that it's second order in time. Why is that so from a mathematical perspective? If it's d squared by dt squared, you're going to need 2 initial conditions. Why? Purely from a maths perspective.
Because you have to iterate twice, you have 2 arbitrary functions or constants.
Yep, beautiful. You have to integrate twice. When you integrate twice, you have 2 constants. Or more, 2 constants, 2 initial conditions. So 2 initial conditions is because you have to integrate it twice. Yep. So why didn't Einstein like the Klein-Gordon equation?
So you have enough initial conditions.
Not enough initial conditions. What is the initial? What is the quantum version of this? So this h of xt equals 0 is to the D'Alembert wave equation what blank is to the Klein-Gordon equation. What is the initial condition for the Klein-Gordon equation? So instead of the displacement of the string at times t equals 0, it will be, have a punt, have a guess. Position, no, we're getting closer though.
The wave function.
The wave function. This is the initial condition. The wave function at t equals 0. And that's not enough. I tell you, for the string, second order equation, the initial displacement is not enough to tell me the displacement of the string at any time in the future. This initial condition is not enough to tell me the wave function at any time in the future. But there's a contradiction here. The wave function is meant to tell you everything you need to know about the quantum system. It's total knowledge. I'm going to demand that the wave function tell me everything I need to know. And it doesn't. Hence, your theory is screwed, throw it in the bin. So that's what Einstein did. Now, I want you to be smarter than Einstein, right? Instead of throwing this in the bin, okay, you've got the benefit of hindsight. You know that this equation is good, right? You know that it works. But I need to get across, and I want you to think laterally here, right? Bit of creative thinking. I make the pessimistic observation, psi must be total knowledge. Knowing psi at the initial time doesn't tell me enough to work out psi at any point in the future. Hence, this equation should be thrown in the bin. There's a negative outcome. Let's be optimistic. Let's be smarter than Einstein. Let's not be so hasty to throw this in the bin. What could we do? Conjugate. We're getting there. If I was to tell you the wave function's complex conjugate, if I was talking to you as I am in the third year lecture, I would say that if you tell me what psi is, you also know what psi star is. And so knowing psi at t equals 0 is equivalent to knowing what psi star is at t equals 0. If I was giving a quantum field theory lecture, the answer would be different. So your answer is correct, but only for a more sophisticated formalism than this. What's your response to that, by the way? Do you buy the argument, or do you want to disagree? Because I like disagreement. I may actually be wrong, by the way. I'm just thinking about this. Can I think about that? You may be right even here, but I can't see how. But I suspect you are right. But I'm confused. Can I just put that on hold for 1 second? So the statement is that psi and psi star could be considered as that you could augment the wave function with psi star. And I'm genuinely stumped by that. I suspect you're correct, but I don't know how to push it further forward. And I can't get past that mathematical argument that you tell me this at t equals 0, then you just complex conjugate it, and you will know psi star at t equals 0. Therefore, there's no extra information here. But I want to be able to shoot down my counter argument, but I can't. Yep. So I suspect you're right, but I don't know how you're right. Is my final answer on that one. Can we think of a different way that we can go forward? You know, the idea of augmenting the wave function. Time derivative. So if you tell me both of these initial conditions, then you've told me two initial conditions, the quantum analogue of this. Hence, this is enough knowledge to be able to integrate the Klein-Gordon equation twice. So what is the wave function? So you've just told me how to solve it, but I still say psi, this thing, is not total knowledge. Therefore, you can't call it a wave function. Therefore, you throw the equation in the bin. What's a better chain of logic, which does not result in throwing the equation in the bin?
That isn't the entire wave function, it's only the wave function at one time.
Yeah, this is not the entire wave function. The entire wave function is psi of RT paired with psi dot. So that's the wave function. Fair enough. That's the wave function. Give it a name. Okay, it's got two components, yeah. Let's call it the Klein-Gordon wave function. It's a function of position and time. And it has two components. This is not a scalar, this is two numbers. This, by the way, is very closely related to a general mathematical thing, that you can reduce second-order equations to first-order equations. To first-order equations by increasing the number of unknowns. Yep. This obeys a second-order equation, the Klein-Gordon equation. This thing, if you work it out, will actually obey first-order equations. I'll let you investigate that further, but a good example is Newtonian mechanics. So let's have the position r as a function of time for a point particle. Force equals mass times acceleration, double dot, yep. That's second order in time. If I don't like the fact that that's second order in time, you know, r at time t equals 0 is not enough. I need to tell you the position and the velocity, r dot. Then you say, all right, r and r dot specify the state of this system. I don't like second order equations. Well, let's give r dot a name. Let's call it v. And force is mass times v dot. This is a pair of first order equations in time. Each equation has one dot, not two, but you've doubled the number of equations in order to get a first order equation in time. And here, the pair r and r dot precisely specifies the state of this single particle system. Now that's a piece of mathematics, which is nice and beautiful, but there's also something very, very profound here. And that's the following. You've got two wave functions now, right? All you wanted to do was to combine relativity with quantum, and now we've got two wave functions. You wanted to have one wave function to describe the electron. That describes an electron. Fair enough. And you wanted to make that consistent with relativity because the Schrodinger equation wasn't going to cut it. And you double the number of wave functions. So we've got two wave functions now. We've got two wave functions, two probability densities. dot, dot, dot. Any speculations as to what's going on here? This doubling of the number of wave functions?
So does one describe the electrons at rest, and one describe it at moving at a certain speed?
So the question, the statement, the response is, does one describe the electron at rest, and does one describe the electron at some speed? And the answers to that's no. It's a perfectly reasonable statement. The reason it's no is because we learned in Schrödinger theory how to get from the wave function to the current. So psi can still have flow associated with it. It's inside the current density. And so psi does not necessarily describe an electron at rest. A second way of arriving at that is, sure, this is fancy relativistic quantum physics, but if your electron is moving slowly, then this thing should obey the Schrödinger equation, and the Schrödinger equation doesn't restrict psi to be stationary, hence in general, psi is not stationary. But this is good, we're throwing up reasons, so we're getting closer to the question of what does this doubling of the number of wave functions mean? Further thoughts? 2 wave functions? Mad guesses? Again, nothing wrong with being wrong.
Maybe one represent the mass of the system, one represent the energy?
Does one represent the mass of the system, one represent the energy? No, because energy and mass are the same thing. Yep. But the more we guess, the more we'll get there. 2 wave functions.
2 observers.
2 observers. I like the first word of that sentence. So 2 wave functions, 2 observers. I like the first word there. 2 wave functions, 2 equations.
2 systems.
2 systems. Oh, we're getting warmer. 2 systems. What are the 2 systems? What's the first system? We started off with a theory to describe an electron. We now have 2 systems. The first system is, and try to remove any clouds of confusion from your mind. Just think purely logically. We began with a wave equation for with a Schrödinger equation for 1 electron. We've been pushed to the idea of 2 systems. The first system is the electron. Positron. Excellent. So that's it, right? So let's look at the logic. I started off with an equation for 1 electron, this thing. Okay, it's in free space, we're ignoring V. We were forced towards 2 wave functions, 2 equations, both of which are first order in time, 2 wave functions, 2 probability densities, 2 systems. The first system is the system we started with, but what's the second one? Doubling of the number of wave functions tells you that there's something else, and that something else is a positron. And the key point here, that was utterly distasteful, right? With this bloody antiparticle. Now, remember, in the mid-1920s, there were 4 particles known to humanity. What were the 4 particles known to physics in the mid-1920s? Well, let me tell you one of them, the electron. 3 more particles, just have a guess. Proton, beautiful. Neutron. 1 more. Photon, fantastic. So these are the 4 particles known to physics. That's it. Mid-1920s. Electron, proton, neutron and photon. But your maths is telling you, and it's coming from the mathematics, there was no physical evidence known at the time, but whichever way you try to cook the marriage of relativity with quantum, whichever way you do it, you always get this doubling of the number of particles, in essence because this E is squared, yep, and E is essentially d by dt, and if you square this, then you're going to get a second order equation in time. Then you have this problem, double the number of wave functions, antiparticles appear. Now here's a very famous quote, so famous that I'm going to write this down. This cannot be taken seriously. So the likes of Klein and Gordon, and later Dirac, Does anyone know who said this about antiparticles? That was Pauli, of uncertainty principle fame. I was reading a history of physics recently, and I was shocked at just how much these people got bagged. They got absolutely hammered. They go to conferences, they get hammered. What the hell is this extra particle that you're talking about? This antiparticle. They got hammered really, really hard. And then Anderson detected the positron experimentally. And I'll post the paper where that was done. But let me just describe it. They get some film. They get a lump of lead and place it across the film. And charged particles from space, they apply a magnetic field perpendicular to the board. And if an electron was coming from the top and a magnetic field was pointing inwards, which way would the electron bend? Magnetic field into the board, electron coming from outer space in a cosmic ray, which way would it bend? To the left? Yep. When it passes through the lead, what would happen? Electron passing through lead. It'll get shielded. It'll slow down. If it slows down, let me exaggerate the radius of curvature here. So the electron's coming in. It's going to slow down. If it slows down, high energy particle, slight curvature. If it slows down, then it's going to be bent more by the magnetic field. So the radius of curvature will decrease. This is a circle with a big radius, let's say big R. But once it goes through the lead, it slows down because of the shielding, and the new radius R prime is reduced. And when Anderson did this experiment, you can actually see these tracks. Again, I'll put it on Moodle. What Anderson saw was this. Bending the other way. So they knew it was positive. Then people could say, well, what about something coming up from within the Earth? But no, when you go through lead, you get slowed down. And so this is going slower than this because it's bending through a smaller circle in the applied magnetic field. So this photograph proved Pauli wrong, and all those who were predicting antiparticles, including those who didn't like them, the mathematics was telling them about this new and hitherto unmeasured thing. This also speaks very nicely about the interplay between mathematics and physics. Maths is you'll never hear me say this, but mathematics is sometimes described as a tool to describe the physical world. I never say that because it's too narrow-minded. Physics and mathematics are absolutely intertwined. Sometimes you use physical reasoning, around which you bolt mathematics to describe the physics. In that case, mathematics is a supporting technology, but the opposite is also true. Physics can inform mathematics, mathematics can inform physics, and there's a balance here. Here, the mathematics was telling very, very clearly, at least in retrospect, about the existence of antiparticles, and people just didn't believe it. Even the people who published these papers were tentative about it, but then Nature came along and said, well, actually what the mathematics was telling you was correct all along. Antiparticles are a very commonplace idea now, but they were immensely radical and disturbing at the time. And so you've just won 2 Nobel Prizes now, so well done, excellent for a tutorial. Thank you, and I'll see you all later.